Okay, so we're ready to get started with the bent part of the experiment. For our VS power supply, we need to get 5.05 volts, and we don't have a transformer that level. So what we have here is a device called a variac. A variac is a variable transformer. It gives you any voltage up to 120 volts AC just by turning this knob. So down to 0, you get nothing out. When you turn it all the way up, you get the full 120 volts out. So it's a variable AC source. I use these for fixing stereos a lot because if you have a stereo that blows fuses, it allows you to bring the voltage up gradually and find out where that extra current is going before you waste more fuses. Very nice device to have. Then we have over here, this is a step-down transformer, so it's going to take whatever voltage is coming out of here and step it down so that we don't have to worry about getting too high a voltage onto our breadboard. So this here plugs into the variac there, and then the two outputs here, we're just going to pick the middle and one of the AC sides and run that to our board. For diodes, we selected the 1N4001. It's a good general purpose diode. They can handle about 2 amps of current, and they're really rugged, and they can easily handle any voltage that this circuit can throw at it. For capacitor, we're using a 220 microfarad capacitor. And then our load resistor, here is our load resistor. This is a 3.9K. It's as close as we can get to 4K without taking out a trim pot. So I'm going to go ahead and start wiring. Okay, we're coming out of our variac into our step-down transformer. And then from the step-down transformer, we want to go to the board. So we're going to plug in our ground wire and route it out of the way here so we don't have too much in the way of spaghetti. And then run that to the ground lead, and the ground lead's connected to this lowermost bus on the breadboard. Okay, and then we're going to take a red wire for our AC voltage and run that to the plus on the breadboard also. And that goes around through this purple wire to the very uppermost lead. And then we're going to use channel 1 of the oscilloscope to look at the input voltage, and then channel 2 is going to be used to looking at the output voltage. So we're going to take this and ground it. And with the scope, you only need to ground one lead. You don't have to ground both of them. And let's just unplug this a little bit and plug that into there. The probe is laying back out of the way, so we're not going to bump against it when we're doing our circuit building. And so the scope is turned on, letting it warm up. We can now turn on the variac, like so, with the voltage. Make sure you turn the voltage all the way down. And then we're going to gradually turn this voltage up and look at what's going on channel 1. So channel 1, we're going to change our horizontal scale so that it'll pick up 60 hertz. And right now it's set for 10 volts per division. We want to set that for 2 volts per division. Okay, and let's set our triggering source on channel 1 so that it holds still on the screen. It doesn't give us a headache. Okay, so there is our AC source. 2 volts per division with the midline right there. It looks like we're at -2, about -3. Let's bring that up a little bit more. That's 4. And that's a little over 5. So right now we have our AC source set. We're getting a nice 5-volt sine wave. Let's spread it out a little bit and turn down the scale. And we have our nice sine wave. And this is a 60 hertz wave that's basically coming right out of the wall. Okay, so that is our VS is working. So now let's go ahead and build our diode. I'm going to temporarily shut this off, even though it's only 5 volts, and it wouldn't hurt to get shocked. So we're going to run a diode from VS. These leads are a little bit thicker down into the field. Let's run that down to here. Get in there, you. There we go. And then we're going to run our capacitor to ground. Note the polarity on the stripe on the capacitor has the minus sign on it. That goes toward ground. So that's going to connect to ground and up to there. And then we're going to put our resistor. The resistor can go in either polarity, also to ground across the capacitor. So this column right here contains the cathode of the diode and the plus end of the resistor and the capacitor. And then these go to ground right there. And let us put our scope probe, on the other side of the diode so that we're looking at the output. And let's turn on channel 2 and see what we get. So channel 2, we're going to also set for 2 volts to 5 volts per division like the other one is, and turn it on. And what we're seeing on channel 2 looks like it's a nice steady DC. So let's just verify that the thing is working. What would happen if we temporarily unplug the capacitor? What we would see is a wave that looks just like the yellow, but about 0.7 of a volt below it. So this is what you get without any filter capacitor in there at all. You can see there's just a little bit of a drop. And then when you put the capacitor back in, you'll see that it fills in the ripples between the peaks in the blue waveform. So let's go ahead and put that back in, and we'll see how suddenly it's all smoothed it all out. So now this looks very smooth, even to the point where we almost can't see the charge side of the ripple voltage, okay? But now we want to take a look and actually measure our ripple voltage and our conduction angle. So to do that, we're going to zoom in on channel 2. We're going to take channel 2 and we're going to connect it to AC coupling. And then we're going to turn the sensitivity way up. And what you see then is your 100 millivolts of ripple right there. Okay? Now you notice this waveform is very spiky and noisy, and so to fix that we can turn on the averaging, and the averaging will, because noise is random, it will average out to 0. So let's do that. Okay? And yeah, we can see that is pretty noisy. So to put the averaging on, you hit the acquire menu, which is always the last place you look. Oh, there it is. Acquire. And we're putting averaging on. And what we'll see is that it cleans up this waveform very nicely. Okay, so now we had all that noise. The noise is random and it averages out to 0. So now we can measure that. Channel 2 is on 50 millivolts per division. And let's slide it down a little bit so that's lined up with the gradations. And what we see is that we're up a little bit, right about there. So one division, that's 50. We're at about 80 millivolts of noise. So we've met the spec for 100 millivolts of ripple or less. So from there to there is 80 millivolts. So we've met the ripple spec. Okay. Now the next thing we'd like to do is measure our conduction angle. So to do that, I'm going to spread this waveform out a little bit further. So we have a little bit more room to measure, and maybe we can slide it over a little bit. Okay. And then we're going to set the 2 cursors. So here's one cursor, and there's the other one. And the cursors, so let's set one cursor over here to the very bottom of the curve, and the other cursor over here to the very top of the curve. Right about there. And so that is the time that the capacitor is charging up between cycles. And so let's measure that time. Here we have a delta is 1.64 milliseconds. So we'd make a note of that. Your conduction angle is going to be 1.64 milliseconds divided by 1/60th of a cycle. This is 60 hertz. So the total period is about 17 milliseconds, 16.7 milliseconds. So we have a conduction angle of about 10% or about 36 degrees. So you just write down this time over here is 1.64 milliseconds. That divided by period, which is 1/60 hertz, is going to give you your conduction angle as a percentage. Multiply that by 360 degrees and you get your conduction angle as an angle in degrees. And that is what you compare with the conduction angle that you calculated using the cosine formula. And that is everything for part A. To estimate the average on current of the diode, it's just going to be your load current divided by the conduction angle. So if your load current is 5 volts over 4K, that's 1.25 milliamps. That divided by the conduction angle, which is about 1/10 of the cycle. So this is going to be about 12.5 milliamps is your average current into the capacitor during this time interval here. And that should be everything you need for part 1.